Howdy, folks. I have a really cool theory. Um, this could probably be a long video again, but I rarely suggest watching this one because it might not make sense at first, but it'll make sense in the end. All right. So, my theory is time is not what we think it is. We think of time as like a human level understanding. I mean, you look at the clock and it says 2:30, right? And you're like, "Oh, I have work at 4:30. I should probably shower and stuff just so I'm ready and not rushed." Right? That is not what time is. That is a human made time. That is a human understanding time. When I say human made, it doesn't mean that I think that we made time. It means that we sectioned it and labeled it. But time really moves in many, many, many ways. For example, whenever you're by a black hole, time moves much slower or much faster whenever you're by the sun or something. Or not, sorry, much slower whenever you're by a very high gravity source. Moves much slower. But whenever you're near almost no gravity, moves much faster, right? That's why we can see some planets have much faster speeds or like much faster days than Earth or any of the other planets in our solar system. Now I got these few pictures right here made. I'm just going to explain them to you. All right, imagine this picture right here, this oval thing, as the universe. Okay? So with this universe, this is kind of what the Big Bang looked like after it exploded, the model we have. Imagine these like little squiggly circles, like really squiggly ones, as like the galaxy clusters, like us, like the stars and all that stuff. And imagine these regular like ovals, smooth ovals, are voids, just nothing, no stars or anything. Time moves much faster in these voids instead of these galaxy clusters because galaxies obviously massive, massive amounts of gravity. Voids, nothing in there, almost no gravity. That's where the theory timescapes comes in from, but I'll say that in another video probably. All right, so I'm gonna do this picture right here. This is the Big Bang. This is the model for the Big Bang theory. Not the show, but this dot right here, this little black dot, that's called the singularity. In the Big Bang Theory, that's where everything started. That's where all the heat and atoms and all that stuff just collected in that very small, small point, a singularity. In this black shaded out section of it, that is the dark energy and dark matter. Whenever you look up at the sky and just see blackness instead of stars, that is probably either dark matter or dark energy. Theory, though. That is the theory. All right. Now, in this section, you see gas clusters. These are after the billions of years, or after, sorry, the millions would probably be more um, understandable. The millions of years, these gas clusters finally found themselves. So, like the four big ones, like hydrogen is one of them, nitrogen, helium, the oxygen, those guys. I don't think oxygen is one of them, but they collected up into these gas clusters. We can see these before, like pre-protostars. Whenever a gas cluster gets like activated or irritated, it will start making this ring, right? A protostar. And then after that point, they start getting activated and stuff. And this is very simplified. After that point, we got the galaxies and stars. This is like the Milky Way or the biggest star we see, Ton 618, I think it's called. And then this is today. This is just the Big Bang, or like today, our universe or whatever. In this section, like I said, dark energy and dark matter. Dark energy was to be seen as the force that is expanding our universe by speeds unimaginable, like light speed. And dark energy, I think, takes about 68% of the universe. So there's about 68% of the universe made of dark energy. Now, dark energy is not matter, so don't take it as you can literally like look up in the sky, reach out, and take energy. The same goes for dark matter. It's just a theory of an understanding. Like we need an understanding on what that blackness is in the sky. Now, for that to work, the Big Bang has to be smooth, like this diagram right here. You see how there's no bumps and stuff? But whenever we see these voids, that's impossible because there's inactivity in here, so it would be smooth. But whenever you see these galaxy clusters, bunch of activity, so there would be a bump, and then probably a bump, and then a bump. It would not be smooth like it is shown. So that's where the theory timescapes comes in. Like I said, I'll probably be brought up in another video, but just a little teaser on that. Timescapes uses the time it takes for things like the redshift. I'll get to that. That's this picture right here. The redshift of a supernova. They measure that and see that it takes a certain amount of time. That's where we get dark energy from. But then scientists start realizing that there was different amounts of times for these redshifts, but the supernova wasn't that far away. And usually supernovas have very similar redshifts, but these ones were like different, up to like the thousandth decimal, which doesn't seem like a lot, but that is a lot. So, like I said, we're gonna get to this. This is a supernova, right? This is whenever a star explodes. So after a star explodes, it can become a dwarf star, which our sun is going to become in like 5 billion years after it becomes a red giant. A red giant, by the way, is the pre-explosion stage. That's whenever the nuclear fusion is on its last leg and it's pumping out and it's just trying to get as big as it can, which means the star is cooling down. It gets this red color, and then finally it into a really little ball, and then it into a supernova. Supernovas have this thing called redshifts. That's what this line represents right here. Redshifts are the light from that supernova and the heat moving off of that supernova. So we can usually measure this time in light years. But, like I said earlier, we're noticing a change in redshifts, which means that this has always happened. I'm sorry, I shouldn't say noticing. Which means that they are not as similar as we thought we did. So the theory I had, I know this took a while to get to, the theory I had was that time is not what we think it is. Okay? Time is not a constant, which means time cannot exist. Like infinity. Is infinity a number or is a representative of a number? We use it in algebra, but that doesn't mean you can do 5 minus infinity and get a plausible answer. So, I don't think time exists on a universal or human scale. I think time is just something we use that doesn't really work. Like I just said, there is no constant to base time off of. There is no default time. Everywhere in the universe, time is different. So that means that 2:30 here would be 5:45 on another planet. We can see this on our planet. What am I talking about? Time zones. I mean, in California, they're 3 hours less than us. So, but I thought that was really cool because with that information, we can start basing things off of physical adaptability instead of the clocks we have. So say we take an average on how easy humans fall asleep. They usually fall asleep around 9 to 10. That's like the regular adult. And they wake up around a certain time. Now, what about in winter, like it is right now, whenever it's dark in the morning and dark at the night, and it gets dark really early? What if we adapt to where our time moves with the weather or moves with the sun? So we wake up in the light days and we do stuff while it's light, and then we go to bed while it's dark, which means we would get better sleep in winter. And it would also mean, which would actually help us getting better sleep in winter because we actually need more energy in winter. So, thank you for listening to my theory. I have really stretched this one out to 10 minutes. I hope you guys have a great day or night, and I will talk to you again. See ya.